Today we're going to look at a cooling curve example. The problem is, use the following data to draw a cooling curve for octane, beginning at 150 degrees C and ending at negative 45 degrees C. Label your axes and indicate the stages as liquid, solid, gas, delta H of vaporization, or fusion. And this table here has all of the important information that you need. So if we are going to draw a cooling curve, we need to start by our axes. So on the y-axis, we're going to have temperature in degrees C. And on the x-axis, we're going to have heat released because we're cooling. So heat will be leaving the system. Now what we need to know is we're starting at 150 degrees C. So that is the first point of temperature that we need. And if you look here, we have 126 degrees C, and we need to get all the way down to negative 45. So we first, as we're going to cool, we first need to reach our boiling point at 126. And the next important point is negative 45. Now we're not actually going to go all the way down to the melting point, so we do not have to plot that. From 150 to 126, we are in what phase? In the gas phase. So we have to draw the temperature coming down. So this is the gas phase. When we're at 126, this is where we're going to go from the gas to the liquid. This is a condensation. And which of these, delta H of vaporization or of fusion, do we have? It is vaporization, so that is the one that we are going to label. Now from 126 to negative 45, we are going to be cooling down, and this is the liquid phase. When we reach negative 45 degrees, that's it, we're done, and this is the curve. Now let's calculate the heat released for the full cooling process above for 115 grams of octane. So we actually need all of this information that we have here. Let's talk about our stages. We have stage 1, where we're a gas, stage 2, which is a phase change, and then stage 3, which is liquid. For stages 1 and 3, we are going to use which way to calculate the amount of heat released? Well, because we're changing temperature, you have to use the one that uses the mass or moles, then the specific heat and change in temperature. For stage 2, we're going to be using the one that incorporates the heat of vaporization. So if we are starting with 115 grams of octane, let's take a look and see if we want to do heat of the first stage. Our M has to match what the C is. So the first stage is gas, and we have moles. So we have to take our grams and convert to moles. How do we do this? 115 grams, and then you have to use your molar mass, which is 114. Remember that this is for grams per mole. So grams, the number goes in the denominator, mole in the numerator. So this is the first part. This is our M. The C, you want to choose the right one for the gas, which is 316.9 joule per mole degree C. Next is the change in temperature. You only want to do the change in temperature for that stage. Remember, change in temperature, delta T, is the final minus initial. The final temperature is 126, and the initial is 150. Also, I want to come back to our... No, just kidding. We're going to keep going. We're good. When you do the math, you should have negative 7,700 joules. If we want it in kilojoules, negative 7.7. And we are good. Now, that's just the first stage. Second stage is the one that incorporates the enthalpy of vaporization. The value of enthalpy of vaporization is in moles as well, so our M must be also in moles. So we basically will bring down what we wrote here, and we're going to multiply it by the delta H of vaporization, which is 41.5 kilojoules per mole. But we're not done, because this enthalpy is for the process going from the gas to the liquid. So heat is released, and we need to show that by the negative sign. When you do the math, you will get negative 41.8 kilojoules. Notice how you have a negative from the first stage, negative from the second stage. If one is negative and another is positive, something's wrong, so go back and look at your numbers. The last stage is the cooling down, the liquid, from the 126 degrees to minus 45 degrees C. And so we again use the same heat release formula as for stage 1. We repeat the conversion to moles as we did in stage 1 and 2. Then you want to make sure you use the appropriate value. Since we're in a liquid phase, use the appropriate value for your heat, specific heat. And it is 254.6 joules per mole degree C. Now we want change in temperature. Again, final minus initial. What's our final for this stage? Negative 45. What is our initial? 126. When you do the math, you should get negative 43,830 joules. If you want to put that in kilojoules, it's negative 43.8 kilojoules. Now, to get the total heat released for the cooling curve, we will add up all of our Q's. When you add them all up, you should have negative 93.3 kilojoules. And again, make sure you pay attention to your sign, because this is a cooling process. Heat will be released, so make sure you check that you have a negative value.